My name is Michael Jones. I'm the managing partner of Subsea Sail LLC. I'm pleased to be here today at the Naval Postgraduate School to talk about our vehicles and our technology and how they apply to U.S. Navy, Marine Corps, people that need energy in various locations. The talk today will be about long duration, energy harvesting and storage, uncrewed surface vessels. So what we're going to talk about today is what we see as the need, which is for affordable, low signature, ocean observation, and then separately cargo and energy delivery and storage capabilities, really everywhere. And one can read what General Berger from the Commandant of the Marine Corps had written in his 2019 planning guidance, which really defined the kinds of vehicles that we have. And it talks about relying on alternative power and allows for indefinite operation. And that is, we think, a very key point. Likewise, Admiral Selby from the Office of Naval Research has talked about often the small, the agile, and the mini, which is what we are developing. But to that, we would also add you want very low operating expense with hopefully negligible infrastructure needs. So our mission as Subsea Sail is to develop autonomous, disruptively affordable, easy to use, and by that I mean easy to put in the water, easy to store, easy to bring out of the water, ultra low signature, 100% energy harvesting, which is kind of the concept around what we're talking about today, and thereby long duration. Vessels, in our case, that can work both above and below water since they have a submerging capability. And since we're talking about smaller vehicles, the creation of unique low swap sensors. So what makes us different? So Subsea Sail doesn't have traditional monohull vessels, and in the upper left-hand corner you can see vehicles that have a traditional monohull. And they have things like hull slapping, and they create wake. And in particular, the bigger vessel, you can see they have a heat, they have radar, they have sound, they have visual, and they have wake signatures. And certainly heat and wake are quite visible from space. So when you look in the lower left-hand corner, you see our observation vessel, which I'll talk about, called Horus. That's about 70 to 80 meters out, pretty hard to find. And then our other vehicle, which is a little bit lower TRL, is our Hermes vehicle, which again I'll talk about. Those are both do not have a traditional hull, which also means they don't need a port. So if you're thinking about how to send something somewhere and not need the infrastructure that bigger vessels have, these are vehicles that really address that. As I said before, they're ultra low signature, so they're very quiet acoustically. They have no heat signature, they have no real radar signature, and they're see-through sails. We're talking about 100% energy harvesting, so that means they're clean. They're low operating expense. Doesn't cost anything to harness the wind. It certainly doesn't cost anything to harness the solar energy. And that allows them to be long duration. This submerging capability that I talked about, the ability to hide underwater from bad weather or bad actors, but also to listen and monitor underwater, we think has real value. And so we are working on a new kind of a buoyancy engine. It's ultra quiet, hard to find. This also creates an opportunity to do electronic warfare, including decoy and deception, by working with our wing sails in a way that allows them to use antennas in perhaps heretofore not easily applicable situations. So we're looking at offensive and defensive CONOPS that we think will be required. As I said, we're really focused on both the CapEx, the capital expenditure, and the OpEx, the operating expenditure. We're looking at the total cost of ownership. And then our Hermes vehicle will be able to carry both traditional and non-traditional loads. Our Hermes E vehicle, which I'll talk about at the very end, would be for energy creation, storage, and then availability, even up on the beach. And the ability for decentralized offshore secure storage, the ability to submerge once you've arrived at your destination so that somebody can't find you, and then you can be called in and you can sail right up onto the beach, again, not needing a port, has real advantages. So I want to talk about kind of sources of energy. One of them is wind. And as you see in this example, there is wind that by the time it gets to the vehicle, if that was ammonia or hydrogen, it's no longer a one-to-one relationship, the way you have in the lower half where you see a sailing vessel that takes direct wind and is sailing with that wind. So it has a series of advantages in terms of using it as a driving force. The advantages include no cost, freedom from fuel. It can be used globally. It also permits point-to-point transit as opposed to traditionally, or more recently, point-to-hub, hub-to-hub, hub-to-point. Energy source 2 that we're currently using is solar. Solar can be highly efficient, and it's, of course, sustainable compared to other green fuels. Solar power is converted from solar energy into thermal or electrical energy. It's clean, it's abundant, it's globally available. Its disadvantage is that it needs good weather, and it's impacted by latitude and the time of year. So on our vehicles, we have significant onboard battery packs that we can use as needed, both above and below water, but there are still certain limitations. Again, low cost, freedom from fuel, global point-to-point transit. As a third energy source from the future, we're looking at harvesting hydrokinetic ocean energy. We're looking at motion-absorbing generators. Hydrokinetic generators that maybe take our sailing movement, and it can use the thruster and back drive to create power when there's sufficient wind. And then, although they're not hydrokinetic, other opportunities, including wind generators somewhere on the vehicle, or even fuel cells. These are future music, as the Germans would say, and they're things that we hope to be working with people like the Naval Postgraduate School to look at these kinds of opportunities for the future use. Our vehicles lend themselves for energy harvesting, and there will be multiple ways to do that in the future. So who are we? We are entrepreneurs. We dream, we innovate, we create. We don't necessarily wait for some kind of a program of record. We have developed disruptively affordable vehicles which allow swarming in fleets, we believe, for the first time. These are minimal signature vehicles, as I talked about before, so acoustically, from a heat point of view, a radar point of view, and visually. They're highly scalable. The vehicle that's there in the middle is actually a vehicle that we sold to the U.S. Army Corps of Engineers several years ago. You can see that blue line where it says waterline. Our vehicle is a semi-submersible, and that makes it really quiet because we have a very low profile as we go through the water. And we have laminar flow, so we don't have hull slapping. We don't push water out of the way a traditional monohull would do. That vehicle is 1.65 meters long. It's 3 meters tall, so about half the wing sail and half the stature underwater. It could take any form factor. We've patented this, so it could look like a whale if you were pre-positioning goods. It could look like a stingray if you had reason for that kind of form, or as it looks like here, an A-frame. Down the bottom are our batteries and a lot of the intelligence. This vehicle is an edge computer. In fact, we have 12 microprocessors on this vehicle. Our second vehicle will be our Hermes, and in the lower left-hand corner you can see this is the Horus vessel, and then we'll have our cargo vessel, which we call Hermes, and then the unique sensors that I referenced before. These are long duration, wind-propelled and solar-powered vehicles, and over time we hope to add other kinds of energy creation. And then this emerging capability we should be fielding on this vehicle by the end of 2023. Communications, when we're close to shore or close to signaling capability of some time, we're talking about cellular, we're talking about Wi-Fi, Zigbee, and then once we go out of line of sight, then we're typically talking about satellite. We have a strong IP portfolio. We have 5 issued US patents and 5 US patents pending, plus other patents pending in Australia and Europe. We're at TR level 7-8 with Horus, soon to be hopefully 8-9. And that is, this month we're deploying a series of new technologies, some of which I'll talk about. It's a 32 kilo, 70 pound vehicle, so it's very easy to deploy and retrieve again. I won't talk about all of our technologies, but again, this is a submerging and righting capsizing vehicle. If it capsizes, it can right itself. That's one of the patents that we have pending. And the depth control of the submersible vehicle. We've received 3 SBIR, Small Business Innovation Research grants, 2 from the Department of Energy, which I'll talk about because they are relevant for both DHS and DoD. And then we have 1 phase 2 from the Department of Energy, which also has relevance for uses in DHS and DoD. We're basically looking for people to work with, whether it's defense contractors, universities like Naval Postgraduate School, people that want to help us understand the ConOps because some of the things we're doing are going to make a difference how the ocean battlefield will play out. So a little more about our Horus vehicle. Horus was the sky god in Egypt in ancient times, and the eye of Horus is known for protection and knowledge. So we thought that'd be a great name for this vehicle. The wing sail that you see here is not just see-through, but it also is hollow. You couldn't go underwater with a balloon under your arm, nor could we. So the idea is here that it'll drain right through, so it becomes essentially neutrally buoyant. When our vehicle goes down, it drifts as opposed to trying to go somewhere. We've also patented our wing sail control mechanism. We do not require an anemometer to know the wind speed, the wind direction, and then a motor to move the wing sail, but rather it all happens passively right on the bottom of the wing sail where there is a cam and a spring that holds it in, and it thereby always is trying to find passively the right spot to be vis-a-vis the wind. And then on the upper right-hand corner, you can see where we'll be working on our buoyancy engine. We've been working on our submerging capability for some time, and in June of 2022, we were in a 2 million liter tank. We signed first ever CRADA, Cooperative Research and Development Agreement, with NOAA and in the Southwest Fisheries Science Center in San Diego. This is a 10 meter by 10 meter by 20 meter tank. And so we went in there, and through their nice portals, we were able to take some pictures. And you can see us going down to 7 meters and hanging out. That's part of what we needed to do to go from the first year of our phase 2 DOE grant to the second year. Why would you want to submerge? Well, there's some obvious things. One is to hide from bad weather. If a typhoon comes along, the ability to go underwater and ride it out rather than being worried about what's going to happen. Of course, if there are bad actors and you want to hide from them, very important. But also important is to be able to listen and to monitor underwater. The ability to listen can be magnified as you get away from anthropogenic and natural noise at the surface, just bubbles and things that are going on. So if you get down to 10 meters or 20 meters or 30 meters, that can be very powerful as you are trying to hear someone coming or someone going. Now that's important in a wartime situation, or just as important is combating what they call IUU, illegal, unregulated, unreported fishing. Our vehicle is very tough. We have been through pretty bad weather. In November, December of 2021, we were out for 31 days. And as you can see here on the left, we went through 2 rather bad storms, rather atypical for San Diego. The wind came down and actually turned the corner and came right around along where Camp Pendleton would be in San Diego. And so we fortuitously were out in some pretty rough weather. This was the second of those 2 storms. And on the left-hand side, kind of in the brown, that was 31 knots of sustained winds. And then on the right-hand side, that little red piece says the wind gusts were up to 35 knots, and we were sailing 1.4 knots. Now to put that in perspective, NATO had an RFI out, request for information, about a year and a half ago, 2 years ago, and they were looking for unmanned surface vessels, one of which they were looking for was a small sailing vessel. And their requirement was that it could function in NATO Sea State 4, survive NATO Sea State 5, and here we were sailing in NATO Sea State 6. So we really have created a very tough vehicle. One of the nice things about Horus, to use that name for it, this is what we would call our semi-submersible monohull vessel. And on both the left and the right, you can see the only thing that really is above the water is that wing sail and just a couple of inches of freeboard. Again, that makes us very difficult to find. So we can work in very light winds and calm seas, or we can work in very heavy wind and high seas. And again, the submerging capability, lots of reasons to deal with that, one of which would be we get over 25, 27 knots of wind, we will probably suggest from a ConOps point of view that the user take that vessel underwater. So this is a bit of a busy slide, but I think it's an important slide because we have received 2 grants from the US Department of Energy. Now their interest was to find, and you can see it right below where it says Department of Energy SBIR Phase 1. The Department of Energy was looking for a low-cost, user-friendly, environmental monitoring and resource characterization tool. And so we received funding, a Phase 1 and then a Phase 2. So in the phase one, we had to show them that we could submerge. I showed that picture a little while ago. We also were working on our acoustic capabilities, and on the right-hand side of this slide, you can see a semi-rigid array that we have been developing with another company. And the idea here is that we can take what has traditionally been two of the most difficult problems in understanding the acoustic underwater. And again, for those that aren't as familiar, above water, we will see things we may not hear. So a truck on a bridge a mile or two away, we'll see that truck, but we won't hear that truck. Underwater, we would hear that truck, not that it'd be underwater, but we wouldn't see it. And so underwater, it's the exact opposite from above water. It really is acoustics, acoustics, acoustics. And so the two problems that typically you have, the real hogs of processing power, are getting rid of extraneous noise, one of which is the hull slapping of a vehicle. And so our case, as I've said, we're an ultra quiet vehicle. And the other need is to understand where your hydrophones are. And in a traditional towed array, you need to see where they are and mathematically figure it out, because if they're looking in one direction, then that submarine or that whale is one place. If they're looking the other direction, it's the other side. So by putting this right on the vehicle, we can eliminate that need to know where the hydrophones are, because we know where they are. As a result of which, our vehicle can process on board. We'll be able to beamform on board and look in certain directions and process and classify on board. So these are things that have never been possible before in a small vehicle. In the phase two, we also, in addition to in addition to the acoustic side, we're also looking at a dual sensor electric field and a magnetic field, so an E field and B field sensor. And there are a number of reasons for that. The reason the Department of Energy is interested is as we put utility level energy creation in the ocean, whether this is wind energy farms or it's hydrokinetic energy farms, we don't really understand the impact on marine life. And so there will be potential for electromagnetic field creation. And we really need to understand how that differs from a baseline of what's being created by Earth, by just naturally. Also, same thing with acoustics. And so there is a recent report, which I'll reference in a second, from NOAA that really talks about long duration monitoring. And a vehicle like ours can do that, again, because of its price point, ability to be put in the water, to do long duration energy harvesting, if you will, monitoring above water and below water. So we're doing a number of things in our phase two, and we're about a third of the way through the 2-year process, and we will be adding essentially acoustics and then E field and B field sensors that allow us to monitor both above water and below water. This is a very interesting slide in the sense that what NOAA has just come out last month, March, with a 388-page report. It's called Fisheries and Offshore Wind Interactions, a synthesis of science, and there's dozens of pages of references. But what's so interesting for us, people ask us whether or not we could do active sonar, and the answer is we could. But usually active sonar, unless you're looking for something specific, let's just say a submarine, where you might be constantly looking, often active sonar is used to do something like the bathymetric, the bottom of a harbor. You might do that every 5 years. Whereas if you're looking at something like the area around an offshore renewable energy farm, you really should be looking for a 25-year period. You should be looking, and this is actually part of the recommendations in this study, two of the major impact factors that they identified in this study were the acoustics and the electromagnetic field. So again, the concern is you put something in the ocean, it creates a lot of new sound that could be disturbing or even worse, be detrimental to marine life, marine mammals, and likewise electromagnetic field. We just don't know. And so the first thing we should do is a baseline testing. And what was so wonderful for us, because we've been saying this for some time, is that the recommendations that have just come out in this new study say we should be looking at a pre-construction baseline testing before you start putting for approvals and then before you put things in the water. And then of course during construction you don't want to have the North Atlantic right whale to be coming when you're pounding in this the jackets for the wind energy, for the wind mills. And so you want to stop that as quickly as possible. That we understand, but we should have that baseline. And then for the next 20 to 25 years when these are working, we should continue to monitor. You know, a new car smells great, of course, and it also is very quiet typically, but 5 years later, it starts having squeaks, it starts having issues. And so something that's put in the water today may be creating more noise, may have more electromagnetic leakage than it has on day one. And so the only way to know that, and the only way to know the interactions, is to continue to monitor over and over again, really consistently over tens of years, 20s of years. And then finally, they call for monitoring both during and after decommissioning. And part of the decommissioning is, okay, what happened? You know, is marine life coming back to that spot? Are they coming back more to that spot? These are all brand new things that we need to learn over the next 20 to 25 years as good stewards of the ocean. So these same technologies that we're developing under funding from the Department of Energy are applicable for Department of Defense and Department of Homeland Security. Give you a sense of how easy it is to put our 70-pound vehicle in the water, 32 kilos, a couple of guys, the captain of one of the vessels that we use, and one of my guys dropping the vehicle in the water, putting the wing sail on, it sails away. So on the left-hand side, you can see, hard to find unless you know where it is. We often will have 3 GPSs on this vehicle, and then as you get out 60 to 80 meters, you see the same picture that I showed earlier, which shows how hard it is to find. I can tell you, because of the curvature of the Earth, when you get out a half a click, about half it's gone, the wing sail, just because of the curvature of the Earth. So the vehicle is very hard to find, and if they do find you and you have the submerging capability, which we're working on, in place, and you don't want to be found, you just go underwater. So our vessels have been created to easily incorporate sensors. And in the top third of this page, we've put on a series of sensors from other companies, including from the U.S. Army Corps of Engineers. They ask us to do leaking explosive ordnance detection. So in this case, UXO. This was down in Puerto Rico. They were essentially transitioning former Navy shelling range to home development, and these people, probably rightly, didn't want to be swimming in a bay where there was a lot of unexploded ordnance. And so initially what they were looking for was leaking explosive detection, and the way they've been doing it was having a couple of divers go out and a couple of people in the boat, and then they would go down and put down a diving bell that had some wafers in it. They'd then a week later come back and pick those up. So it's very labor intensive. And they had a little bit of problem figuring out where it was that they were picking this up, and they didn't know necessarily where the leak was coming from. We could go right from the dock and gather this. We could go sector by sector, come back to the dock. They could pull out the wafers, take them to the lab, and do their work without ever putting anybody at risk. They also want to do a turbidity sensor. So we used things that they wanted us to do. More importantly is when you get down below that kind of long line, we worked with a partner company, Applied Ocean Sciences. We've created new kinds of passive acoustic monitoring arrays that work natively on our vehicle. And we've created something called PAMELA, which is our DAC, Digital Acquisition Unit, that allows us to take up to 8 analog acoustic signals in and 4 digital signals. So we've got really strong capabilities to do onboard processing. And now we're in the process of creating a masthead electronics, and everything we're building now, because we will be submerging, needs to be able to submerge down to 100 meters. So it will be rated to 100 meters, but tested to 150 meters. That makes it hard on us. It's not as hard to have something that works on the surface, what they would call IP67 or 68. When you say, I want to go down to 100 meters, you're talking about a lot of pressure. You know, most of our cars have 34, 35 pounds of pressure. If you were to go up to 150 pounds, it would blow out your tire. And yet that's what we're subjecting our equipment to at 100 meters. We're going to put a whole bunch of stuff in the masthead electronics. You can't see it, but on the right-hand side, We're going to have GNSS in addition to GPS. We'll have a 6-color camera with classifiers, an anemometer, not because we need to know that for our wing sail, but rather because of our to have it for METOC purposes, for weather purposes. So there's a lot that we're going to pack into this little masthead electronics. We have dramatically upgraded our Horus vehicle. You can see it's April 2023, and here we are in April 2023. We are this month really introducing a whole series of new features in our vehicle. Now, we've been working on this vehicle for over 4.5 years, so this is a big step forward to us, and it's a very exciting moment. And I'll give a couple of examples because there's a number here. In the right-hand corner, upper right-hand corner, you can see a box. That box is hermetically sealed. And we have pins on the outside, but we don't have penetrations the way typically is done. And then they have full ocean depth kinds of connectors, but if you rupture the podded nature in the acrylic, then water can get in, no matter how good the connectors might be. So we've actually hermetically sealed that computer box, which has got a lot of processing in it. We've also driven the power consumption down so that our power on this vehicle is dedicated to sensors and not to the management of the vehicle. That computer box, for example, uses approximately 1 watt, which is almost unheard of. The lower right-hand corner, you can see our wing sail. It is a similar form factor what we had before, but we've now moved away from a carbon fiber mast to a Kevlar mast. And instead of carbon fiber around the battens, we are going to molded fiberglass. That gives us both advantages in terms of how light it is, but it also means that we can allow the customer, if they are so inclined, to do electronic warfare related activities, including passive monitoring and active development of decoys and deception kinds of opportunities. So we're really doing a lot to make our vehicle as flexible as possible for our customers, which will be, really across the board. It'll be academia, it will be industry, it will be government and military. Again, upper left, you can see same look and feel as before, weight, but far more capable, and everything has to be able to submerge to 100 meters. So this is a big step forward for us. Even our batteries, we've now come up with a different chemistry. It's a little bit like you go into the store and you see a battery pack that says 10-year shelf life. 4, 5, 8 years ago, that didn't exist, but they're working with the chemistries so that the decay rate is very low. If I'm going underwater, I want a very low decay rate so that I can stay underwater longer. Also in this vein of what we have upgraded, I mentioned our batteries, low decay rate. Our PAMELA, which is our DAC, our digital acquisition unit, will not only is very low power usage. It starts off at 1.1 watts, but running full time, including classifying acoustics, it's pulling only about 1 watt. It started out at 7.5 watts, so we've worked really hard to get that usage down. But we're also going to allow users that maybe have some very proprietary technology or something that maybe is classified to put their board inside our DAC. And that way they'll be able to use our power and our communications, but no one except they will know, because it's encrypted, what's on that vehicle. We have a flooded cone, and then right behind the cone on the left-hand side, it says sensor slices, and that's where we're going to make it very easy for people to put new sensors on the vehicle. We think that's really important, that we are trying to look at the total cost of ownership. So rather than having to send back to us the vehicle and say, hey, I need some new things on it, you're going to be able to essentially install those on the vehicle. On the right-hand side, we already talked about the hermetically sealed craft computer box. We're putting now Iridium Certus on the vehicle, so it's a high-capacity Iridium as opposed to Iridium SPD, small burst data. We have our servo and an improved housing. We're now creating an auto-leveling ballasting system, so right between the batteries that can move back. So if you put something in the front, a new sensor, which could start out at 1 or 2 or even 4 inches, might otherwise create a nose forward kind of a situation, not sail well. the ability to pull that back by having this ballasting is very important. So now you're saving time for the people that are deploying this rather than spending a half a day just balancing the vehicle before you put it out. And finally, we have a new thruster motor and a controller and a new ultra-low noise propeller as well. Something we're very proud of, we're essentially creating a digital twin. And right in the middle of this slide, you see it says interface unit. The idea is that a developer or a student would be able to work on new sensors right in the classroom and then take it to the vehicle and put it on, and it will be accepted as if it was native on there. So the idea is to make it really simple rather than put something on and figure out if you've weighted it correctly, then go out and see if it works, then come back in. Again, you could spend days experimenting. And our hope is by doing this, again, this is in development for us, but very much all the software, all the hardware is being developed to move in this direction. So multiple universities, multiple labs could be working together on a new sensor or something, some capability, and then essentially be looking at it as if it's a digital twin, and then taking it out, putting it right on the vehicle. I'm going to transition just for a few moments to our other vehicle, our Hermes vehicle. So we call it Hermes, and I think most people know Hermes was the winged god. He had wings on his helmet, he had wings on his sandals, but he was also the god of commerce. And we believe there's a need, and I set this right up front, the need that we see is one is for observation, really being everywhere around the world, and the other one is to be able to deliver small loads in many, many places where you could put maybe 50 vehicles out, particularly if you're going to be pre-positioning or resupplying people that don't have access to a port. So you could go right up on the beach. So the great advantages of multi-hold vehicles is that they're fast. The fastest sailing vessels in the world are multi-hulls. They can carry a lot, and they have the ability to go right up on the beach. Anybody that's ever been to a resort has probably seen Hobie cats, and those Hobie cats are right on the beach. So those are the three great advantages. The one big disadvantage for multi-hulls is they capsize. When they get to about 45 degrees, they have a tendency to want to go upside down, as we would say to turtle. So we've got some technology patent pending that we think will address that. We believe that these kinds of vehicles are ideal for expeditionary forces, for humanitarian aid. Most of us don't know that when we give money to Save the Children or UNICEF, that 60 to 80% of every dollar goes to delivery. So if we can drop that dramatically when you have a $25 billion humanitarian aid kind of budget around the world, and you could save 1 or 2 or 3%, we're talking about hundreds of millions of dollars. But more importantly is we could deliver to people on the shore rather than try and move them into refugee camps, maybe because the only place you think you can deliver is near an airport or near a port. So we call this future music. We're right now at a TR level 5 on our way to TR level 6. We received phase 1 funding from the National Science Foundation, which has allowed us to work on this particular vessel, this capability. We're looking for phase 2 funding to let us take it to the next level. So I talked about multi-hull vessels, the advantages. So we think by using smaller vehicles, we can de-risk the supply chain. I mentioned it before, but I'll reiterate it. If you're talking about an area where you are going to deliver humanitarian aid, it is probably an area that's had a tsunami or a typhoon or even a war situation has gone through and has destroyed the port. And one of the reasons we fly a lot in is because even if all the buildings at an airport have been destroyed, the very flat concrete runway is still there. And so we can sweep it off and we can fly whatever it is in. Think of the Berlin airlift as just an example. It's not very efficient, it's very expensive. So if we can deliver right to the beach, even better. But the two things that have happened in that port, not only is the equipment to load and unload the vehicle, but it's also all the storage is gone. And so the ability for us to go somewhere, again, I've said from the beginning that our vehicles will be able to submerge. So when we go and are offshore, we will be able to submerge down to somewhere between 30 and 100 meters and hold that position. Again, that's good if you're worried about the situation you're in, whether that's bad weather or bad actors. The ability to have offshore, secure, underwater, decentralized storage could be very important. We look at these as multi-use platforms. They can work with traditional cargo, if you will, from a Navy parlance, beans and bullets and Band-Aids, but also things that you could put underneath the wings, almost like an aircraft. Those could be leave-behind assets for someone else, or it could be a tube-launched loitering munition. It just depends on what the need is. So our vehicles, we think, have many applications, and you can see in the lower left, cargo delivery, a communications gateway, data gathering sensor packages, and then an unmanned aerial vehicle or quadcopter landing, a UUV delivery docking with recharging. So lots of applications, but the reason, the fundamental reason that we can deal with this is the upper left where you see the 1, 2, 3. We have 3 patents pending on this in the United States and other countries, one on the heeling wing sail to prevent the capsizing. The most important one, I would say, is the ability to load level as people take things out of the AMAs, the outside AMAs, or the cargo area, but also the ability to flip the vehicle over and come back to the surface and take off again. If you look in the lower right-hand corner here, you can see some upside-down vehicles, or ones that have capsized. And although it's a little small, I'm sure, for the viewer, the lower right, when the trimaran has got a guy sitting in the middle waiting for help, and the top of those 3 pictures has got 3 guys standing on the lower pontoon. And so the problem with multi-hulls, again, I talked about the 3 advantages. They're fast, they can carry a lot, and they can go right up on the beach. The one great disadvantage is the fact that they can flip rather easily. So by having created a way to submerge the vessel, right itself underwater, come back to the surface, and take off again is really brand new. And so we believe then we can create smaller vehicles, and many of those vehicles that can do pre-positioning or resupply, even into contested areas. So this is on the left-hand side, you can see a vehicle, and there are some mock things underneath the arms. Above them are solar panels. So we're an energy creating unit. Now in this case, we don't have any solar panels on the wing because we don't believe we'll need that. This is just a 4-foot by 4-foot prototype, just to look at it. We'll probably be building at least 15-foot by 15-foot. And my last slide will actually address that. So again, we have some technologies that we think bring forward this opportunity to resupply to people that need that. Again, whether it's humanitarian aid, inter-island delivery, or expeditionary forces. My last slide, the Department of Energy has been promoting a really interesting concept calling powering the blue economy. Their interest is having significant amounts of power in the middle of the ocean or wherever it's needed. And we've created a concept vehicle, and then the 4 variations here, 15-foot by 15-foot, that we think could have about 1.5 kilowatts peak power, 20-foot by 20-foot, 3,000 watts, and so on. So it just depends on what you're looking for. But the ability to go right up onto the beach now means that you could have clean power. You don't need to put a generator and then deliver fuel, which then creates a heat signature for somebody that's looking down. But rather, you've got a very clean way to deliver energy, even to the extent that you could go into the hulls and pull out energy packs, maybe for night goggles or for something you're carrying, and then put in the ones that have already been depleted, let them recharge, and do that process over and over again. So this kind of a concept vehicle is really to show the power of our Hermes vehicle, that it will be able to take multiple forms. So while we don't have the time or probably the interest to listen to all of the ideas that we're having, this at least is one on the energy side, and I was really pleased to be invited by the energy group here at Naval Postgraduate School, because they were trying to understand more about our vehicle and how it could work, what kind of con-ups people could make with that. And so for us, it's a great opportunity to talk about all of our vehicles with different groups at the university, but in particularly the energy academic group, the EAG, looking at this vehicle. And again, everything about our vehicles is 100% energy harvesting, so it fits in beautifully, very efficient in that we're using direct wind, direct solar, and the other things that we'll be looking at in terms of power from the ocean, movement, et cetera, all will be direct, renewable, completely clean energy that allow us to go long duration and do things that in places in ways that we don't think anybody's ever worked before. So thank you for your attention, and if anybody has any questions, all my contact details are there, and it was wonderful to be here at Naval Postgraduate School. Thank you very much.